Cohesion between water molecules results from the polar covalent bonding found in the water molecule itself. The water molecule is made up of one oxygen and two hydrogen atoms sharing electrons in a covalent bond. The situation is that the oxygen attracts electrons towards itself more so than does the hydrogen. Because electrons are negative, if they're being attracted towards the oxygen, this leaves the oxygen with a slightly negative charge and the hydrogens with a slightly positive charge. Because of this charge distribution, the bond is therefore known as a polar covalent bond. If you then consider that this applies to all water molecules, it's easy to see how one water molecule can attract another one. You can have the slightly positive hydrogen being attracted to the slightly negative oxygen, and this forms a hydrogen bond. The two water molecules being attracted to one another is known as cohesion.
Polar covalent bonding can also attract water molecules to other molecules. This process of attachment of a substance such as water to the surface of another substance is known as adhesion. This simple demonstration using a beaker, dyed water and a capillary tube demonstrates capillary action, which is the movement of water within the capillary tube in part due to the forces of adhesion and cohesion. We can observe here that when the capillary tube is placed inside the beaker, the water rises from the water level in the beaker up into the capillary tube. Capillary action occurs when the adhesion to the walls of the capillary tube by the water molecules is stronger than the cohesive forces between the water molecules. This is significant because the cohesion between the water molecules and the adhesion between the water molecule and the surface allow the water molecules to move up the narrow capillary tube in the same way that they're able to move up the xylem in a plant. It is through the xylem that the water moves from the roots of the plant up to the leaves. As the first molecule moves up, it pulls the second water molecule because they are attracted by a hydrogen bond.
Two thermal properties significant to living organisms are that water has a high specific heat capacity and also a high latent heat of vaporization relative to other liquids. In this simple demonstration, we're heating up oil on the right-hand side and water on the left-hand side, and you can see from the graph that the oil increases in temperature a lot quicker than the water does. This is because water has a higher specific heat capacity than the oil. That means it takes more energy to change water's temperature by a given amount than it does for oil. Therefore, water can absorb a great deal of heat before it starts to change temperature, and so you can see in this demonstration that its increase in temperature is at a slower rate than that of the oil. Water's ability to absorb a great deal of heat without changing temperature as much as other substances also relates to its high latent heat of vaporization. Its high latent heat of vaporization means that it can absorb a great deal of heat when it evaporates or changes from a liquid to a gas. As a result of the polarity we just discussed, water is an excellent solvent of other polar molecules. A solvent is a substance that dissolves a solute, where the solute is a chemically different solid, liquid, or gas. In this simple demonstration, I'm dissolving salt, NaCl, which would be the solute, in water, which is the solvent. The salt, NaCl, is made up of the ions Na+ and Cl-. It dissolves in the water because the Cl- is attracted to the slightly positive hydrogen ion, while the Na+ is attracted to the slightly negative oxygen ion.